Imagine an object so bright that it outshines every star in its galaxy combined. Something so powerful that it can be seen from more than 13 billion light-years away across an expanding universe. And imagine that this brilliance, this blinding cosmic beacon, is not a star at all, but the death scream of matter spiraling into a supermassive black hole. Welcome to the world of quasars, the brightest engines the universe has ever created. But here's the part that still terrifies scientists. Quasars shouldn't exist the way we see them. They ignite too early, grow too fast, and shine too intensely for our current physics to fully explain. And yet the James Webb Space Telescope continues to discover more of them, bigger, brighter, and stranger than anything predicted. A quasar begins with a feeding black hole, not a small one, not even a typical galactic supermassive black hole. We're talking about monsters millions to billions of times more massive than our Sun. When these giants find themselves surrounded by enormous streams of gas and dust, everything changes. Gravity drags the material toward the black hole, forcing it into a spinning, superheated disk. Friction, magnetism, and extreme compression raise the temperature of this disk to hundreds of millions of degrees. At that heat, atoms tear themselves apart. Matter becomes plasma, and plasma becomes light, more light than entire galaxies. But here's the twist. The black hole itself emits no light at all. Everything we see comes from matter desperately trying to escape its fate. And yet the closer that matter gets to the event horizon, the brighter it becomes, releasing energy with insane efficiency. Up to 40% of its mass can be converted directly into radiation. For comparison, nuclear fusion, the process powering all stars, releases less than 1%. That means a feeding black hole is the brightest, most efficient power source in the universe. But that raises a terrifying question. If quasars are so powerful, why don't they blow themselves apart? Why doesn't the radiation they produce stop the inflow of gas and shut the engine down? Yet somehow quasars maintain a delicate balance, feeding, glowing, and launching jets for millions of years. This is only the beginning, because the deeper you look into a quasar, the stranger the physics becomes.
To understand why quasars are so blindingly bright, you have to travel deep into the accretion disk, the swirling inferno around the black hole. Picture a hurricane made of superheated plasma, rotating at nearly the speed of light. Every orbit, every ripple, every collision inside the disk releases staggering amounts of energy. But brightness alone doesn't make quasars unique. It's their behavior, violent, chaotic, yet somehow stable, that shocks astronomers. The innermost region of the disk glows so intensely that it drowns out starlight from an entire galaxy. Surrounding stars become invisible silhouettes compared to its furious brilliance. But the true monsters are the relativistic jets, two gigantic streams of charged particles that erupt from the poles of the black hole. These jets travel across millions of light-years, cutting through intergalactic space like cosmic blowtorches. They move so fast that time itself slows down for the particles inside them. And here's where things get truly mind-bending. These jets shouldn't exist. Classical physics says nothing should escape a black hole's gravity, not even light. Yet quasars generate jets that outrun entire galaxies. The explanation lies in the black hole's magnetic fields. As matter spirals inward, magnetic lines twist tighter and tighter, forming enormous electromagnetic rails that accelerate particles to nearly light speed. This process is so powerful that it can reshape the galaxy around the quasar. Some quasars sterilize star systems with radiation. Others ignite bursts of star formation by heating gas clouds. They are cosmic architects, creators, and destroyers. And still, the biggest mystery remains. How do they turn on? What triggers a black hole to suddenly feed so aggressively that it becomes a quasar? Many scientists believe the answer lies in galactic collisions. When two galaxies crash, enormous rivers of gas flow straight into their central black holes, igniting quasar activity. But Webb has revealed quasars that formed far earlier than any collisions should have occurred. Quasars that appear fully grown when the universe was only 700 million years old. That's not enough time for a black hole to reach 1 billion solar masses, unless something far stranger happened. Could some black holes have formed directly from collapsing primordial gas clouds, or existed since the earliest seconds after the Big Bang? The mystery deepens with every new observation.
Now follow the journey of quasar light across the universe. A photon emitted near a black hole's event horizon travels through billions of years of cosmic evolution before reaching our telescopes. It passes through clouds of hydrogen, weaving through the cosmic web, bending around massive clusters, slipping between forming galaxies. Each of these interactions leaves a fingerprint, tiny distortions that scientists can measure. That makes quasars the most valuable tools for exploring the young universe. Their light reveals when hydrogen first became ionized. It maps the invisible structures of dark matter. It exposes ancient chemical signatures formed by the first stars. But there's another layer to this story, one scientists barely understand. Quasar brightness fluctuates, sometimes slowly, sometimes rapidly. But some quasars dim and brighten in ways that defy their size. Objects billions of kilometers wide shouldn't change brightness in a matter of days or weeks, yet some quasars do. This variability hints at turbulent structures within the disk, massive waves, magnetic storms, or even orbiting clumps of matter spiraling inward. And then there are the hyperluminous quasars, objects like J21573602, which consumes the mass of a full star every day. This breaks the conventional Eddington limit, the theoretical maximum brightness beyond which radiation would blow the disk apart. But these quasars don't blow apart, they grow, which means our understanding of black holes is incomplete. Adding to the mystery, some quasars appear in galaxies too small to host such massive black holes. Others show signs of having formed before the first known galaxies. Webb engineers expected to find fewer quasars as they looked deeper. Instead, the opposite happened. They found more, and some are impossibly bright. So either black holes grow faster than we think, or the early universe had unknown mechanisms feeding them. Or, most shocking of all, some black holes didn't form from stars at all. They may have been born massive, primordial, ancient. And if primordial black holes exist, they could explain not just quasars, but also dark matter.
The final and deepest mystery of quasars is not their brightness, but their origin. How do black holes become massive enough to power these incredible engines so early in cosmic history? The universe was young, chaotic, and still forming its first stars when the earliest quasars appeared. They needed enormous black hole seeds, far larger than anything created by stellar collapse. Scientists propose 3 radical ideas. First, direct collapse black holes, giant primordial gas clouds collapsing straight into black holes without forming stars. These seeds could reach 100,000 solar masses instantly. Second, runaway black hole mergers, small black holes colliding repeatedly inside dense star clusters, growing faster than expected. Third, primordial black holes, objects formed directly from quantum fluctuations after the Big Bang, potentially millions or billions of solar masses from day one. If primordial black holes exist, they could be scattered across the universe, hiding as dark matter. And when one of these giants finds itself inside a young galaxy, its feeding frenzy triggers the ignition of a quasar. But there's one more twist. Quasars don't live forever. They burn bright for a few million years, then fade into silence as the black hole exhausts its fuel. When that happens, the galaxy it inhabits continues evolving. Stars form, planets appear, life, perhaps, emerges. And at its core, a silent black hole remains, waiting for the next wave of gas to awaken it again. One day, even our Milky Way may flare into a quasar if enough material falls into Sagittarius A star. The night sky would turn white, glowing with radiation from the galactic center. And from billions of light years away, another civilization might look at our galaxy and see what we see now, a blinding cosmic lighthouse powered by a hungry black hole. That is why quasars matter. They are not just bright objects, they are messages from the universe's childhood. They tell us how galaxies grew, how black holes evolved, and what unimaginable forces shaped everything we see today. To understand quasars is to understand the universe itself, and every new discovery brings us closer to answering the oldest question in astronomy. How did something so bright come from something so dark?